This example is one of the hardest it gets, so if you understand this then you're fine. We've got a particle on a rough inclined plane, so I'll just draw that on, and there's the particle, and it's got mass 5 kilograms, which means this is a weight of 5g, and the angle here is theta. I don't know what theta is, but I do know that theta is arc sine, that's just a way of saying inverse sine, sine to the minus 1 of 3/5. So that means that sine theta is 3/5, and you might be thinking, well, that's not very helpful, is it? But there's a little trick that you can do. If this is theta, sine is the opposite over the hypotenuse, so this is 3 and this is 5, and using Pythagoras we can get this to be 4. So that means that cosine theta is 4/5, and if I need it, not likely, but if I did, tan theta is opposite over adjacent 3/4. So this is a standard way to give you the information about the angle, where they're not actually telling you the angle, but it lets you get sine theta, cos theta and tan theta from it without ever finding out what theta is. Okay, back to our picture. We've got the 5g going down. The coefficient of friction is an eighth, mu is an eighth, and there is some string and there is a pulley, and then there is something falling down like this, and this one is got a mass of 4 kilograms, so that's 4g there, and it's a light inextensible string, which means the acceleration of the second particle will equal the acceleration of the first particle. And what else do we know? Oh, the friction will act down, mu r, and we've got our normal reaction there. And this is 2 meters above the ground. 2 meters. And we want to find the acceleration. Okay, let's start. Usual thing, let's break the two particles into separate problems. R and 5g. Let's resolve that 5g into here's the angle here, so that's 5, that's the same as that angle, 5g cos theta, and downwards, sorry, not down there, down here, 5g sine theta that way, and 5g cos theta that way, and that's the components of the weight force. And then we can do our equations. We've got resolving perpendicular to the plane, because it's not accelerating, perpendicular to the plane, so r equals 5g cos theta, and then using F equals ma up the plane, we get t minus mu r minus 5g sine theta, that's the F, that's in the direction of the acceleration, equals the mass times the acceleration. Okay, we can put in our mu, we know what that is, t minus, what was it, 1 over 8, 1 over 8, and we know what r is, it's 5g cos theta, minus 5g sine theta equals 5a, and we know what cos theta is because we worked it out earlier using the little trick, it's 4/5, and sine theta is 3/5, so we can put them in as well. T minus 5 over 8g times cos theta, 4/5, minus 5g times sine theta, 3/5, equals 5a. Might be able to tidy that up a little bit more. Oop, it's going over there. Never mind. So we've got t minus 7 over 2g equals 5a. So that's all we can get from that particle. Now let's look at the other one. So the second particle has the weight 4g, it's got the same tension because it's a smooth pulley, it's accelerating this way, no direction in which to do equilibrium, so we'll do F equals ma downwards, that gives us 4g minus t is the mass, which is 4 times the acceleration. So if we combine these two pieces of information, this one and this one, that gives us 4g minus t, which is 5a plus 7 over 2g, equals 5a. And if we solve that, we get half a g equals 10a. So 1 over 20g equals a. And if we do that to two significant figures, we get 1 divided by 20 times 0.8 is 0.49 metres per second squared. Now the next part of the question is actually a CVAT, the time which elapses. So I'll just write out my ingredient. We want the time. We've just found the acceleration. I'm going to use this as positive, so it's accelerating at 0.49 metres per second squared. And the initial speed was 0, and I know that the displacement is going to be 2 metres. So I want the equation without a v in it, which is s equals ut plus a half at squared. So we get 2 is no lots of t plus a half times 0.49 t squared, which gives us t is 2.857 seconds. So that's how long it takes. Now here's the bounce bit of it. This is the bit that sometimes throws a lot of students, but it's worth quite a lot of marks, and once you've got your head around it, it's okay. So the movement of P up the plane is as follows. It goes up while the Q is falling down. Then there's the moment when, do this in a different colour, red, there's the moment when Q hits the floor, which is when P is here. And then P has momentum. Momentum is mass times velocity, and it's got some mass and it's got some velocity, so it keeps going for a little bit. So it's actually got some more movement like that. And then it will come to a halt, and then it will probably go back down and to where the red square is, and then that's where it will stop. But the total distance P moves up the plane is all of this. So we're going to work out how far that is in two sections. Now this one's easy, because this is the same distance here as the Q moves down here, which is 2 metres. So this is 2 metres. And so now what we need is how far is this. Now this is going to be a SUVAT, so let's think how much of the SUVAT we've already got. Let's take, we're doing the SUVAT up the plane, so this is going to be our positive direction. We want to know how far it's gone. The final velocity will be 0 because it's when it comes to a halt and starts going back down. Time, don't really care about. U, don't know, and A, don't know. So these are the two things we need to think about. If we can get one of the, no, both of these we need to get both of them. Okay, so let's think about the acceleration. During the period of movement when it goes from the red bit to the blue bit, this is a force acceleration diagram. This is what's going on. We've got the weight, 5g, we've got the reaction, r. The weight, 5g, can be split up into 5g cos theta and 5g sine theta. And there is nothing pulling it up anymore because the Q has landed. So this is just moving by its own momentum. So there's nothing going up the hill, and that is all of the forces apart from, I forgot, friction. So we've got friction as well, which is mu r. So if we do, and it's accelerating, well, it's accelerating down the hill, but I'm going to use up the hill as positive. So using F equals ma, up the hill, then we get minus 1/8 of r, minus 5g sine theta is 3/5, equals the mass 5 times the acceleration. And we know what r is because, sorry, running out of room here, resolving perpendicular to the plane, r equals 5g cosine theta. So putting those together, putting the r is 5g cosine theta into here, and then solving this, we get a for the period of time that the particle P is moving without being pulled. And a really common mistake is to put this a in here, but this a is only what's happening for this period of time. This period of time it's a different situation, because instead of having tension in the string, the particle P now doesn't have any tension in the string. So solving that, we get a equals minus 1.372, and that's what goes in here, minus 1.372. Now what about U? I need to know how fast it's going at this point here, but this is the end of a SUVAT on this period of time. So I think I'm just going to delete some stuff and have some space here. Much better. Right, now, how much information did we have? We're interested in this bit of time here, and it's the S that we want to know. We found the A is minus 1.372, that's because we're taking up the plane to be positive. The V is 0, we're not interested in the T, how much time it takes, and we need the U. So, thinking about the U, we do a SUVAT on this bit of time here. That's how we get our U. So U is the speed it's going when it's red, as I've coded it here. So I'll take plus like that again. The initial velocity is 0 because at this point it's 0. Then the final velocity is the thing that we want because that's the velocity here, which is the final velocity of this bit, but the initial velocity of this bit. A, we worked out, is 0.49 up the plane, and the distance that it travels from here to here is the same as from here to here, which is 2. Now we can use the formula without t, which is v squared is u squared plus 2as. And then solving that, we get v squared equals 0 squared plus 2, 0.59 times 2, which gives us v is 1.4 meters per second. So the 1.4 meters per second is the final velocity of this bit of movement, which is the initial velocity of this bit of movement, and then that feeds in here. We did another SUVAT, don't forget, which I've now rubbed out, so I'll put that here to remind you. We did another SUVAT, sorry, not a SUVAT, we didn't do a SUVAT at all. We did an F equals ma on the section of movement from here to here. So it looked like this. It had forces like that. It was accelerating down the hill, so we ended up with an F equals ma. Solving that, we got A equals minus 1.372, and that is what fed in here. And we know that when it gets to this point, it's got a velocity of 0, that's the whole point. It goes up with its own momentum, slows down, stops, and then goes back down again. Now, what do we need to know? Nothing, I think we're done. We can find S. So we need the formula without t, which is v squared is u squared plus 2as. And then we stick everything in, so 0 equals 1.4 squared plus 2 times minus 1.372 times s, which is what we're trying to find, which gives us s equals 0.714 meters. That's your final answer. So the structure here is always the same. You're basically doing a SUVAT on the bounce. This is the bit I call the bounce. You're doing a SUVAT on the bounce. You might be interested in the distance, you might be interested in the time. Your u here, this one, this u, is v for this period of time, so you can get that from a SUVAT on this period of time because you've already found the acceleration. And your a must come from an F equals ma on this section of the movement where there's no tension pulling it up. So it's a difficult problem and there's lots of ingredients, but it's always the same structure. So if you understand it, you can practice using it and get used to it that way.